بالله من الشيطان الرجيم بسم الله الرحمن الرحيم.
The project of the custodian of the two holy mosques, King Fahd bin Abdul Aziz Al Saud, to extend the mosque of the Prophet, peace and blessings be upon him. The midday sun beats down on the plains and hills that encircle the holy city of Al-Madinah Al-Munawwarah in the Kingdom of Saudi Arabia. In summer, the daytime temperature in the region exceeds 50 degrees centigrade. In winter, the weather is wet and cold. Visitors converging on the Prophet's holy mosque to pray within its precincts have had to endure these climatic extremes over the centuries with a minimum of relief. However, this is set to change. For the first time, there's to be a regulated, controllable climate throughout every area of the mosque. This film tells that story. Today, the Prophet's Mosque comprises three distinct areas. The Old Mosque, encompassing the Blessed Rada, and crowned by its famous green dome. The King Abdul Aziz extension, built around two large courtyards and completed in 1955. And the recently constructed extension of the custodian of the two holy mosques, overseen by King Fahd bin Abdul Aziz. From the outset of planning work on the current extension, King Fahd wished to incorporate an air conditioning system to help regulate the temperature within the Prophet's mosque and increase the comfort of visitors. Sophisticated analysis had revealed that 45% of the heat generated inside the mosque would be given off by its visitors. 33% would come from the climate of the region, and the remaining 22% would come from equipment and lighting needed to run the building's support services. Each human body generates 1 kilojoule of heat, equivalent to a 100-watt light bulb. This is multiplied many thousands of times over by the worshippers gathered in the enclosed spaces of the Haram. Perspiring bodies in unregulated temperatures would create dangerously high levels of humidity. The air conditioning system therefore needed to be capable of dealing with these factors efficiently by providing a constant, controllable climate in the three different areas of the Prophet's Mosque. The new extension around the existing mosque would increase the size of the building fivefold to 82,000 square meters, enabling the project's engineers to incorporate the air conditioning system into the initial designs of the building. Integrating the climatic control equipment into the two other existing areas of the mosque would be a more challenging and demanding assignment. Successful regulation of the temperature within the Haram was dependent on the enclosure of all areas of the building, including the two large open courtyards of the King Abdul Aziz extension. Likewise, the installation of the ducting, vents and equipment for the air conditioning system had to be done without destroying the tradition and character of the existing mosque. The air conditioning system depends on several key elements. A central station to house the plant and machinery capable of chilling thousands of gallons of circulating water a minute. Pipes to transport the chilled water to the mosque. Fans to draw fresh air through filters from outside the building into air handling units. These units cool the clean air by drawing it across copper tubing containing the chilled water and are located in a large basement area under the new extension. A network of steel ducting and vents to transport the conditioned air beneath the marble flooring to the columns for diffusion into the mosque. Retractable covers and shading structures to enclose the many open courtyards of the mosque. When closed, these would help maximize the efficiency of the air conditioning system. When opened, they would allow the warm, used air inside the building to escape through the roof. Chilled water is produced on a purpose-built central station in the foothills of the mountains that ring Medina. Located 7 kilometers to the southwest of the Haram, the site houses a chilled water complex to service one of the largest air conditioning systems in the world. Central to the operation are 6 chillers installed in a specially designed building. These are made from high-grade steel to withstand the high compression levels and temperatures generated within the system. Outside the chiller building, 6 fan-cooled condensers were constructed. After installation, each condenser was tested to ensure that the intricate piping network could contain the high pressure needed to operate each chiller effectively. The chillers cool the used water returning from the Haram basement by means of the vapor compression cycle. A volatile liquid flows into an evaporator, where it acts as a refrigerant, circulating around copper tubing containing the warm water. This causes the refrigerant to vaporize by extracting the heat from the water through the copper and cooling it. Now in gas form, the warmed refrigerant is drawn into a centrifugal compressor, where its pressure is raised, which in turn greatly increases its temperature. The compressed vapor then passes to a condenser, where the refrigerant discharges its heat to the surrounding air and turns back into a liquid. This liquid flows through piping and into an expansion valve, which causes the high-pressure liquid to expand to a lower pressure. This reduces its temperature still further as it re-enters the evaporator, enabling the vapor compression cycle to begin again. The water circulating from the chillers to the Haram basement and back is kept in a sealed system. To maintain the high pressure, which could alter as the pipes expand or contract in the fluctuating temperatures, the system can be topped up with mains water held in a tank under pressure by compressed air. The used water returns from the haram basement to the chiller at a temperature of 18 degrees centigrade. Entering the evaporator, the warm water passes through a network of copper tubing 2 centimeters wide, which is exposed to the low-pressure circulating liquid refrigerant with its temperature of 6 degrees. The warmth of the water causes the volatile liquid to vaporize, transferring its heat to the gas and cooling down to the lower temperature of the refrigerant in the process. The chilled water leaves the evaporator to go back to the haram basement, whilst the gas needs to be turned back into a liquid so that the vapor compression cycle can continue. The gas passes into a centrifugal compressor. A 5,200 kilowatt electric motor and gearing drives the centrifuge, which compresses the refrigerant to 19 bar. This raises its temperature to 66 degrees centigrade. The gas is forced outside the chiller building in piping to the 6 condensers. Each one has a surface area of 360 square meters, making this rig the largest air cooling condenser system in the world. 8 fans draw up air around the refrigerant as it passes below, through 3 layers of narrow gauge tubing. The fans turn at 200 revs per minute, and the updraft of air is enough to lower the temperature of the refrigerant to 50 degrees centigrade, just above the ambient air temperature. This causes the gas to lose its heat. By the time it reaches the bottom layer of tubing, the refrigerant has turned back into its liquid form. Still under high pressure, the newly formed liquid passes back into the chiller building and through an expansion valve on the chiller. This expansion lowers the pressure of the liquid, and as it expands, it rapidly reduces its temperature, so that by the time it re-enters the evaporator, it has fallen to 6 degrees centigrade, and the cycle begins all over again. Each chiller can produce 230 litres of chilled water per second. Leaving the evaporator at the desired temperature, after its exposure to the refrigerant, the chilled water supply is pumped back to the haram basement via the utility tunnel. By locating the central station 7 kilometers from the haram, it became necessary to devise a means whereby the chilled water supply could be safely transported from the chiller building to the air handling units in the haram basement, and the warm used water